Good morning, one and all. Myself, Vaidegi, working as assistant professor in Sri Muthukumaran Institute of Technology in EC department. Today, the video lecture is from the subject EC 3452 Electromagnetic Fields for the 4th semester ECE students. In this video, we are going to see the topics of vector integrals, gradient, divergence, and Gauss divergence theorem. Vector calculus connects calculus with geometry in three-dimensional space. Unlike ordinary calculus, where we deal mainly with functions of one variable, vector calculus allows us to study fields that vary in space. In electromagnetic theory, quantities like electric field and magnetic field exist at every point in space and charge from one point to another point. To analyze such fields, we use integrals and differential operators. The three important integrals we study are line integrals, surface integrals, and volume integrals. Each one gives us a different physical meaning. Together, they help us measure accumulated quantities, flow through surfaces, and total quantities inside region. First, we see about the overview of vector integrals. Vector integrals extend normal integration into higher dimensions. In one dimension, integration under area gives a curve. In two or three dimensions, integration helps us measure physical quantities distributed over curves, surface, or volumes. Line integrals are used when quantities are distributed along a path. Surface integrals are used when quantities pass through a surface. Volume integrals are used when quantities are spread throughout a three-dimensional region. In electromagnetic fields, these integrals help calculate work done by electric fields, electric flux through surfaces, and total charge stored inside a region. First, we see what is line integral. Line integral is performed along a curve in space. It can be applied to both scalar fields and vector fields. When applied to a scalar field, it calculates the accumulated value of that scalar quantity along the path. In surface integral are used to integrate vector fields over two-dimensional surfaces in three-dimensional space. The most important physical meaning of a surface integral is flux. Flux represents the total amount of a vector field passing through the surface. In volume integrals, it extends integration into three-dimensional regions. They are used to calculate total quantities distributed throughout a solid region. Next, we see about the line integrals of scalar and vector fields. When we perform a scalar line integral, we integrate a scalar function along the arc length of a curve. This represents accumulation of a quantity along a path. In contrast, a vector line integral calculates the dot product between the vector field and the differential displacement vector. This represents the work done. The dot product ensures that only the component of the force in the direction of motion contributes to work. If the force is applied perpendicular to motion, no work is done. This idea is very important in electromagnetics when analyzing electric forces of charges. Next, we see about the surface integrals and flux. Surface integrals measure flux through the surface. The mathematical expression involves vector field dotted with the differential surface element. The normal vector plays a crucial role because it defines orientation. If the field flows outward, the flux is positive. In inward, flux is negative. In physics, this concept is applied in fluid flow, heat transfer, and especially electromagnetics. For example, electric flux through a closed surface is directly related to the charge enclosed inside that surface. This forms the basis of Gauss law. Next we see about the volume integrals and their applications. Volume integrals are widely used in electromagnetics. If we know charge density inside a region, integrating over the volume gives total charge. Similarly, integrating energy density gives total stored energy. In symmetric systems like spheres or cylinders, spherical or cylindrical coordinates simplify calculations. Understanding how to choose coordinates is very important for solving EMF problems efficiently. Next we see about the gradient of a scalar field. The gradient is an important operator that acts on a scalar field and produces a vector field. It is represented by the symbol del. The gradient points in the direction of maximum increase of the scalar function. Its magnitude represents the rate of change in the direction. For example, in temperature field, the gradient points towards the direction of maximum temperature rise. In electromagnetics, electric field is the negative gradient of electric potential. This measures the electric field always points in the direction of decreasing potential. Next we see about the divergence of the vector field. Divergence operates on a vector field and produces a scalar. It measures how the field spreads out from a point. If divergence is positive, the point always behaves like a source. If divergence is negative, it behaves like a sink. If divergence is zero, the field is called solenoidal. In electromagnetics, the divergence of a electric field is proportional to charge density. Magnetic fields have zero divergence because magnetic monopoles do not exist. So, divergence tells us about source and sinks in the field. Next, we see about the Gauss divergence theorem. Gauss divergence theorem connects volume integrals and surface integrals. It states that the volume integral of divergence over a region is equal to the surface integral of the vector field over its boundary. Physically, this means total surface strength inside a volume equals total flux leaving the surface. This theorem is extremely powerful because it converts difficult volume integrals into simpler surface integrals. In electromagnetics, Gauss law is directly derived using this theorem. It connects the differential integral forms of Maxwell equations. Next, we see about the summary of the concepts we have seen in the previous slides. In this lecture, we studied line integrals, surface integrals, and volume integrals. We also understood the gradient and divergence operators. Line integrals measure accumulation along paths. Surface integrals measure flux through surfaces. Volume integrals measure total quantities inside regions. Gradient tells direction of maximum increase. Divergence tells source or sink strength. Gauss theorem connects local and global properties of fields. Together, these tools form the mathematical backbone of electromagnetic theory. Next, we see why these concepts are used. These vector calculus concepts are not just mathematical tools, they are the language of physics and engineering. They are the language of physics and engineering. Maxwell's equations are fully written using gradient, divergence, and curl. Fluid mechanics, heat transfer, and electromagnetics all depend on these operators. Mastering these fundamentals will make advanced EMF topics very much easier. Students, I hope you all understand about these concepts. Next we see in the next lecture video. Thank you.